Welcome to The Explainer. Have you ever stopped to think about how kind of magical it is that your voice or a song on the radio can just travel across cities, countries, even oceans? Well, today we're going to unpack that magic. We're diving into the fundamentals behind radio, TV, and so much of our modern communication. So here's the game plan for this explainer. We're going to start with the basic problem. How do you send a signal a really long way? Then we'll uncover the brilliant trick engineers figured out to solve it. And finally, we'll explore the different ways that solution is still used all around us today. Okay, so let's jump right in by looking at the fundamental challenge here. Why is sending information over long distances so hard in the first place? It seems like it should be simple, but it's actually a massive engineering hurdle to overcome.
This diagram here is basically our map for this whole journey. You see, information starts at a source, goes through a transmitter, travels across a channel, like, the airwaves, gets picked up by a receiver, and finally lands at its destination. But for that long-distance travel to actually work, there's a crucial step missing right inside that transmitter box.
And before we get to solving the problem, let's just make sure we're on the same page. At its heart, what is communication? It's really just the process of getting information from point A to point B through some kind of medium. Simple as that.
And here it is. This is the core problem. The raw signals we want to send, like the actual sound of a human voice or music, are what we call baseband signals. They're naturally low frequency, and they just don't have the oomph to travel very far on their own through something like the air. They basically run out of steam and fade away almost instantly.
So, if our weak little message can't make the long journey all by itself, how in the world do we get it where it needs to go? The answer is an incredibly clever trick, a brilliant piece of engineering called modulation. So what is modulation? In the simplest terms, it's the process of stamping our low-frequency message onto a really powerful high-frequency wave. We call this the carrier wave. This carrier is strong enough to travel huge distances, and it essentially gives our original message a piggyback ride. Now, modulation isn't just a one-trick pony, it's like the Swiss Army knife of communications. Sure, it gets the signal from A to B, but it also solves a ton of other practical problems, like shrinking antennas from being literally miles high to something small enough to fit on your car. And, maybe most importantly, it's what creates separate lanes on the information highway, so your favorite radio station doesn't just bleed into your neighbor's phone call. We're going to come back to that idea. In this chart here, it illustrates the two main families of this technique perfectly. We can either modulate the carrier's amplitude, which is its power or strength, or we can get clever and modulate its angle, which deals with its frequency or phase. Let's start with amplitude first. All right, let's tackle our first method, amplitude modulation, or AM. You've definitely seen this one before, right on your car radio dial. It's actually one of the oldest and most straightforward ways of doing this. The idea here is really simple. You take your high-frequency carrier wave and you just vary its power, its amplitude, so that it perfectly traces the shape of your original message. The speed or frequency of the carrier wave stays exactly the same, only its strength changes. And what's so cool about this slide is you can actually see AM in action. Look at that top wave. That's our original message, maybe our voice. Now look at the signal below it. The peaks and valleys of that fast carrier wave now form a perfect envelope that is an exact outline of the original message. Pretty neat, right?
You can think of AM as the Model T of radio. It was absolutely revolutionary because it was simple and cheap to build. It just got the job done. But that simplicity comes with a price. It's a total gas guzzler when it comes to power, and it takes up 2 lanes on that frequency highway when it really only needs 1. And that inefficiency is exactly what pushed engineers to find a better way. Okay, so we've seen how you can vary a carrier's power. But now let's just pivot to a totally different strategy. What if we keep the power constant, but instead we play with the timing, the rhythm of that carrier wave? And that brings us right to the second major family, angle modulation. This class includes something you're probably very familiar with, FM radio, which of course stands for frequency modulation. So with angle modulation, the amplitude, the power of that carrier wave, stays completely constant. All the information is instead encoded in these tiny, super precise changes to its frequency. That's how fast the wave is wiggling. Or its phase, which is just a subtle shift in its timing. And this is why it really matters. Think about most of the noise you hear, like static from a lightning storm. That stuff is an amplitude thing. It shows up as big spikes in a signal's power.
Since angle modulation encodes information in frequency and basically ignores changes in amplitude, it's naturally way more resistant to that kind of noise. That is exactly why FM radio usually sounds so much clearer and cleaner than AM. Now, while frequency modulation and phase modulation are like close cousins, they ended up finding very different jobs. FM became the undisputed king of analog broadcasting, but phase modulation and its digital relatives became absolutely essential for high-speed digital stuff. We're talking the backbone of technologies like your cell phone's data connection and your home Wi-Fi.
Okay, so we've figured out how to send one signal, and send it well. But how does the entire planet handle millions of phone calls, thousands of radio stations, and just countless data streams all at the exact same time without it all turning into one chaotic, jumbled mess?
The answer is a concept called multiplexing. The best way to think about it is turning a single country road into a huge multi-lane superhighway. It's the whole set of tricks that lets tons of different signals share the exact same channel.
I know this diagram looks a little technical, but the idea behind it is actually really simple. See on the left? Each one of those messages is like a car waiting to get on the highway. Each on-ramp uses modulation to put its message on a unique carrier frequency. That's like assigning it to its very own lane. Then, all those signals, each in their separate lanes, merge and travel together down that common channel. That's our superhighway. On the other end, the receiver uses filters to sort all the cars back into their original lanes, making sure every message gets to the right exit.
So let's just bring it all home. The one fundamental concept that makes our entire global communication network possible is modulation. It doesn't matter if it's by changing a wave's power, like an AM, or its rhythm, like an FM. This one big idea of giving our small messages a piggyback ride on a powerful carrier, that's what lets our voices travel across the entire globe. So I'll leave you with this thought. The next time your Wi-Fi is acting slow and you go into your router settings to switch the channel, what you're really doing is finding a less crowded lane on the data highway for your signal. You are literally using the exact same principle, frequency division multiplexing, that was pioneered for analog radio over 100 years ago. The DNA of these old ideas is still the absolute backbone of our most advanced technology today. Thanks for joining this explainer. Keep asking questions.